Good afternoon, everyone. Welcome to week 7's problem solving sessions. I'm Shreya, one of the TAs for the course, and today I'll be discussing a few problems based on week 6 lectures and also on week 7 lectures. So, before I get started, can you please confirm if you can see my screen?
Yes, ma'am.
Alright. Fine. So, last week we learned about three very important discrete distributions which were binomial, Poisson, and we learned about geometric distributions. We also learned in what context these are used and what is the CDF or what is the PMF, probability mass function, how to characterize these, what could be the mean, what could be the variance, and so on. These things we learned. So I'll solve a few more problems on these distributions, and then we'll move on to week 7 lectures. So consider this one. Let's say x, y, and z are three stochastically independently distributed random variables with binomial distribution such that x, y, and z is this, then what will be the distribution of x plus y plus z? Now, one thing you have to note here x follows binomial n equal to 15, p equal to 0.25. Y also follows binomial m equal to 5, p equal to 0.25, and z also follows a binomial where n is 20 and p is 0.25. Now the first step 1, you have to see and notice that these p's are same. Okay, so if these p's are same, then you can write that if this is same for all the individual variables that you are considering, then x plus y plus z would follow binomial a sum of these numbers, sum of the n's. So this one plus this one plus this one, so it would be 15 plus 5 plus 20, and p would be 0.25. Alright, so your answer in this case will be binomial 40 p 0.25. Is it okay? Alright, okay. Next we have this one. So here we have, let's say we have number of defective bytes in a hard disk has a Poisson distribution, and average number of defects per millimeter squared of the hard disk is 0.2. Surface area of the hard disk under study is 120 square millimeters. Determine the probability that 10 or fewer defective bytes occur in the surface area of the hard disk under study. Now how should you write x? Let x be the number of defects in what is your area under study, that is 120 squared millimeters. Okay, and any kind of defect usually is modeled as a Poisson distribution. Okay, because defects are rare events. Here it is already mentioned, it has a Poisson distribution, so we need not worry. But usually whenever something like a rare event or a defect thing is there, whenever we are modeling defective items which could be countably infinite and the probability of getting that defect is low, then we say that usually it follows a Poisson distribution. So whatever, okay, so then X follows Poisson some lambda, where lambda would be average number of defects in this area under consideration, 120 millimeter square. Okay, now so what will be our lambda? Average number of defects per millimeter squared is 0.2. So in 120 millimeter square, how much would be the average number of defects? It would be 0.2 into 120, so it would be 24. Okay, so then X follows Poisson 24. Then probability that 10 or fewer defective bytes occur would be probability X 10 or fewer, meaning less than or equal to 10. Okay, so how will you calculate it? Using R, you would have to give P poise and then you have to enter the parameters. What were the parameters? Do you remember? Okay, can you see the R console here? Okay, I have one more request. So what happened last 2 weeks, I suddenly got logged out and I couldn't realize I was logged out of the conversation because I mean only I was speaking. So I would request all of you to kindly unmute yourself and tell me, so that I don't have to switch screens and look whether I'm there still connected with you all or not. Okay, and since there are very few people in this meeting, would really like it to be interactive. Alright, okay. So we wanted this thing, probability X less than equal to 10. So this could be done using P poise. So what we'll do, we'll write here P poise, and then what we have to mention here, the X equal to 10. Okay, and lambda would be 24 and lower dot tail would be true. So it would be 0.001. Alright. Okay. So moving on. If I have to find this thing, find the number of defective bytes in a hard disk has a Poisson distribution. Okay, same question, determine the probability that 15 or more defective bytes. So here also we have X following Poisson 0.2 into 120, that is Poisson 24, and we have to find the probability X is greater than or equal to 15. Okay, so what we could do, this we can write as 1 minus probability X less than 15, which would be 1 minus probability X less than equal to 14, because X can only take integer values. Remember, X is countable, it's defects. You cannot have half a defect. Okay, if you have defective bytes, half byte defect you cannot say. So sorry, so here x less than 15 means the maximum x can attain is 14. It cannot go beyond, because if it crosses 14, the next number is 15. Okay, so then what we'll write 1 minus p Poisson. This number would be 14, lambda would be 24, and lower dot tail would be true. So we'll just do this. So p Poisson 14, lambda equal to 24, lower dot tail equal to true. This is 0.198, and we are going to do a 1 minus. So the answer should be 0.98. So this should be 0.98. Now, if you are not sure whether how or what to use, then you can always do this thing. So in order to double check whether we are getting this same result or not, what I can do, (1 to 14) b Poisson d Poise I 24. Okay, so I'm going to check whether this matches with 0.198 or not. So now what is my sum value? This is also 0.198. Alright, so the main point that I want to repeatedly tell you is that whenever you use in R, we have to be very careful when we are considering discrete distributions. If we give P distribution name, distribution code, and then the parameters, and then if we give lower dot tail equal to true, then we get what we get is P x less than or equal to whatever q we mention over here. Alright, but if we give P, then the distribution code q, and if we say lower dot tail equal to false, then we get P x greater than q. Okay, strictly greater than q, which is x greater than or equal to q plus 1. Okay, so accordingly, if you if this was the question where you had to find out 15 or more, or the question was more than 15 defective bytes. So let's say we had this question that we have to find out probability x greater than 15. Then we could have directly written P Poise 15, lower dot tail equal to false, lambda equal to 24. This would have given me the answer readily. But since here we have an equal to sign, we also have to take that x equal to 15 probability into consideration. Okay, so be very careful while while you solve these sort of questions, what is written. If it is at least or strictly greater than, strictly lesser than, what does the question imply, and accordingly you have to solve the questions. Okay, am I clear? Okay, alright. So this question says that it has been established that number of defective LED produced daily is Poisson distribution distributed with mean 5. Over a 3-day span, what is the probability that the number of defective LED lights does not exceed 6? So here again we have to consider a 3-day span. So x should be the random variable that number of defects in 3 days. Okay, then x also follows a Poisson lambda equal to 5 into 3. Okay, so this would be Poisson 15. Then probability number of defective lights does not exceed 6 means probability x should be less than or equal to 6. It shouldn't exceed 6. So this would be same as p poise 6, 15, lower dot tail equal to true. Okay, so we'll find out what this becomes. So we'll write here p poise 6, 15, or I'll write here specifically q equal to 6, lambda equal to 15, lower dot tail equal to true. So that would be 0.007. This one 0.0076. Alright. Okay. Okay. So here it says if 4% of the components of an electrical equipment are defective, using Poisson approximation to the binomial distribution, what is the probability that 15 out of 500 circuits will have defective components? Okay, so what is this Poisson approximation to binomial distribution? Suppose x follows some binomial np, and when n is very large, then x can be approximated by a Poisson distribution. Okay, and what would be the parameter lambda of this Poisson distribution? Anybody remembers? NP, correct. So this lambda would be NP. Okay, and also this thing I should tell you, n is very large and p is reasonable small, okay, such that NP is finite. Okay, this criteria, it's anyway it is maintained, but we should take care of this. Okay, n is large, p is usually small, and then NP is finite. In such cases, the binomial can be approximated with a Poisson distribution. Okay, now what is the question? 4% of the components of an electrical equipment are defective. Okay, using the Poisson approximation, what is the probability that 15 out of 500 circuits will have defective components? So x is how much? I mean, how should I define this random variable x? X is number of defective circuits. Alright. So here we have to find out probability x equal to 15. So this would be, we have to use the Poisson approximation, probability x equal to 15. So this would be e to the power minus lambda, lambda to the power x by x factorial. Okay, so this you can calculate, e to the power minus, your lambda will be, n is how much, 500, and p is how much, 0.04. So NP will be how much? NP would be 20. Okay, so this will be e to the power minus 20, 20 to the power 15 by 20 factorial. Another, so you could either calculate this, or you could just do in R. If you have to do it in R, then you have to do a dpoise. Dpoise 15, 20, and that would give you the result. So we are going to do that. Where is the cursor? Can you see it? Ha. So dpoise x equal to 15, lambda equals to how much? Lambda was 20. This is 0.0516. That is our answer. This one, 0.052. Okay. Alright. Moving on. So, which of the following alternatives can be an outcome of the command rpoise n equal to 8, lambda equal to 7? Okay. So, here we are drawing n equal to 8. That means there should be at least 8 numbers. So, well, let us count 1, 2, 3, 4, 5, 6, 7, 8. This has 8. 1, 2, 3, 4, 5, 6, 7. This is out. 1, 2, 3, 4, 5, 6, 7, 8. This is in. 1, 2, 3, 4, 5, 6, 7, 8. This is also in as a first step. Okay, step 1. Step 2 is, it should be a positive integer. Okay, so then this one is cancelled, and this is also cancelled. This is a decimal point and this is a negative number, negative integer. So the question is, the only correct answer is answer 1. Is it okay? Alright. So this says, which of the following command in R will compute probability x less than 8 where x follows a geometric distribution with the parameter p equal to 0.7. Okay. So in R, geometric distribution is modeled as x equal to number of failures until first success. Okay, so probability x less than 8 is probability x less than equal to 7. Okay, so then to find out this less than equal to x7, the command is p, and for geometric the code word is geom. So it would be p geom 7 0.7. That is this thing. Okay, d geom will give you what? D geom is going to, if I give d geom 7 probability equal to 0.7, then it is going to give me probability x equal to 7. Okay, it is not going to give me less than or greater than. It will give me the mass at x equal to 7. Alright. So, shall I move on to the next one? Okay. Here again the question is, a customer help center receives calls on an average of 3.5 calls every hour. What is the probability that it will receive at most 4 calls every hour? Okay. So, this we are going to find out what can be a suitable distribution for this thing. So, do you think a binomial distribution is going to work over here? If I, let's say my first choice is binomial, but binomial can't work because n has to be finite. There has to be n number of calls that is determined. Okay. So usually in such cases at a call center, number of calls that you are going to let n be the total number of calls. Okay. This one is usually large. Okay, and you cannot even say that okay every day or today I'm going to at the beginning of the day you cannot say that okay today I'm going to receive 100 I'm going to get 100 calls. Okay, whether I'll receive or not, that's a different thing, but I'm going to get 100 calls, but that is also a very large number. So this one, number of trials, this thing, it doesn't go well with the question. Okay. The next thing is Poisson. Does a Poisson distribution fit well? Yes, a Poisson can fit well because this receives an average 3.5 calls every hour. If I assume also that it could follow a binomial distribution, since n is usually large, it can be approximated with the Poisson distribution. Okay. And geometric is what? Number of failures or number of attempts till first success. Here we are not determining that how many number of calls or how many attempts should one person make before someone receives the call. The question is not like that. So the most appropriate distribution that we can fit is usually in such scenarios is the Poisson distribution. Okay. So then if x is the number of calls received, every hour, okay, so then it follows a Poisson distribution with lambda equal to 3.5. Alright, then what will be the probability that it receives at most 4 calls every hour? This means probability at most 4. That means x should be less than or equal to 4. It will not receive more than 4 calls. That is at most. So this will, how will we get it? Again we will do p poise 4 3.5 lower dot tail equal to true. Okay. And the second part is, what is the probability it will receive at least 5 calls? This is probability x greater than equal to 5. So this one is equal to probability x greater than 4. So here for this we will write p poise 4 3.5 lower dot tail equal to false. Okay, is it clear? All right. Okay, thank you. All right. Again, a similar question. A person receives emails on average 3 emails per hour. Here also the question is very similar to that call center question. So here again we are going to model X as number of emails received per hour. Okay, then X follows. No, the question we have to see first, what is the probability he will receive 5 emails or over a period of 2 hours. So let X be the random variable, which is number of emails received in 2 hours. Okay, then X would follow a Poisson. Mean would be 3 emails per hour. So over the period of 2 hours it would be 3 into 2, 6 emails. Okay, so this would be Poisson 6. Then again same thing, what is the probability he will receive 5 emails over a period of 2 hours, exactly 5 emails, that is X equal to 5. For this we'll write d poise 5 lambda equal to 6. Okay, and probability he'll receive more than 2 emails, X greater than 2, this would be p poise 2 lambda equal to 6, and the most important thing is lower dot tail equal to false. All right. Poisson. Yes. All right. So let us move on to this one. Here they are saying mass produced needles are packed in boxes of 1000. It is believed that one needle in 2000 on average is substandard. So what is the probability that a box contains 2 or more defectives? Okay, so mass produced needles are packed in box of 1000. So here you see maximum number of defects can be 1000, so there is a cap. So if I say X is number of defects in a box in a box of 1000 needles. Okay, so here what is my N? N is 1000, which is undoubtedly large, but still this is fixed. Even though my random variable is defects are, I am calculating defects out of a box. So the number, if I say X, if I define the event that getting a defective item is a success, then that can happen. I mean, I am calculating the number of successes in 1000 trials. I am looking at 1000 needles.
Hello,
Yes.
madam,
Yes.
Can I disturb? Madam, just a minute. Like, what will be the examination pattern, main exam pattern? The proctored exam which we are doing, that pattern, the pattern, do we have any pattern for that? Question paper pattern?
Question paper pattern, this will be similar to the assignment problems that you are doing, but exact pattern I'm not really aware of. So you can contact the NPTEL team to get to know more about the exact pattern from like how the questions would be there. But I did not get you.
Like pattern question paper, for every exam there will be a question paper pattern, whether
Yeah.
it is multiple choice questions or descriptive type. What kind of this thing? it will be online or written or something like that. Because I'm taking it for the first time. I'm not aware of that also.
Okay, so you can do one thing. I would suggest you write to the NPTEL team and they would tell you what the exact pattern for this semester would be. Okay, so as far as I am aware of, there are multiple choice questions, but it could change also. I cannot give a concrete answer on that. So it's better if you contact the NPTEL team and they would give you what sort of questions we would have and whether it would be online or there would be a test center. Okay.
No, the test center is there, but whether there also it will be online, whether it has to be like an exam.
I would request you to get this confirmed from the NPTEL team directly.
Okay, ma'am.
Okay, thank you, sir. All right. So these are mass produced needles. So where was I? So I am trying to look at the total number of defects in a box of 1000 needles. So this is identifying a defective item is my success event. So then X follows a binomial N and P, where N is 1000 and P is the probability of getting a defect, and that is given here. One needle in 2000 on average is substandard. So this is 1 by 2000. Alright, so this you can write as binomial 1000 1 by 2000. Alright, in order to find this out, you can directly apply the binomial this one. If you want to find out two or more defective x greater than equal to 2, you can just write it as 1 minus probability x less than equal to 1. This would be 1 minus p binom n equal to 1000, p equal to 1, q equal to 1, and what were the parameters? Let us just check. So if I want p binom, q was 1, size is my n, so size was 1000, probability would be 1 by 2000, and lower dot tail will be true. Alright, so here you could get this directly as well. Now another thing, if you notice here, this n is fairly large and p is very small, such that np is finite. Okay, so x follows, let's say binomial 1000 and p is 1 by 2000. So this is small and this is large, and np is half, which is finite. Okay, so you could also use a Poisson approximation. Okay, so then this x could also, you can write it as, it follows lambda equal to half. Okay, and then the required probability x greater than equal to 2 would be 1 minus probability x less than equal to 1, and that would be, so if I do 1 minus p Poisson, q equal to 1, lambda equal to half, and lower dot tail equal to true, then also I am getting close result. See, for this one was 0.09 016608 and this is 0.0902 0401. So up until the third decimal place it is the same. Okay, so this approximation works well. I mean, this is one validation that uh, this Poisson, whenever we have a n which is crossing, let's say 500 or 1000, usually we would have good results. Alright. Okay. Fine. So this was all about discrete distributions. Okay, I did not discuss about the discrete uniform distribution today, I mean the sums on that, but we have found out that dunif command. So, okay, so the what I am talking about is the discrete uniform distribution. Okay, where at, let's say, if I have a to b, a plus 1, a plus 2 to b, at each point I have 1 minus b minus a probability, this one, this one, this one, this one. Okay, or let's say I do not 1 by b minus a, I'm sorry, I have 1 by n probability, such that if there are n points including a and b, and each point has probability 1 by n. Okay, so such distributions were modeled with a discrete uniform distribution. So now we'll move on to, so this was discussed during week 7 lectures. We learnt about continuous random variables. Okay, continuous random variables means these variables can take any value in the real line. Okay, there could be bounds, some could only take positive values, some could only take negative values, but they can take any value, not only integer values. All right, so those kind of random variables are known as continuous random variables, where x is said to be continuous. And we learned that for any continuous distribution, point probabilities are 0. Now why so? So let's say you have this continuous distribution. This is your fx, which is the probability density, and this is your x, and you have a graph like this. So what were the two properties of any PDF? Fx should be greater than equal to 0 for all x, and integration fx dx should be 1. So what it means is that the total area under this curve should be 1. Alright. Now, whenever I am talking about probabilities, so I am talking about area under the curve. So this thing, the total probability is 1. So if I let's say if I want to find out, let's say this is my distribution function, something like this, from a to b, if I want to find out probability a less than x less than b. Okay, so this one I'll be able to find out fx dx from a to b. So essentially what I'm trying to do is that I'm trying to find the area under this curve between points a and b. Now let's say you have a very very small, I mean let's say this is your curve, okay, and you want to find out probability at this position b. Okay, so this exact area under this point to this point is actually 0. Okay, so for any point on this axis, if I want to find an area that, let's say this one, So area under the curve between this A point and A point is 0. Actually there is no area. What we can assume is that there is a very small boundary around B. Okay, so let's say this is B minus epsilon to B plus epsilon, and we can measure what is the area between these 2 points. But at any particular position, if we have to find out the point probabilities, this is always 0. Alright, so this is one point to remember, that point probabilities for all continuous distribution is equal to 0, because there is no area that we can calculate. Alright, okay, then we learned how to calculate CDFs from PDFs. So in order to, if you are given a PDF of any sort, then integration minus infinity to x ft dt would give you the CDF. Capital Fx is the CDF of the graph. Okay, and then we learnt about distributions like continuous uniform distribution, normal and exponential. So we'll just briefly discuss. So if you have a continuous uniform distribution, the distribution looks somewhat like this. So you have 2 points, let's say A to B, and this is this is, let's say, your Fx. This is 1 by B minus A from A to B, and at all other points Fx is 0. Okay, so this is how a continuous uniform distribution looks like, and we know expectation of x would be A plus B by 2, and variance of x is given as B minus A whole square by 12. Okay, and again you see this Fx dx from A to B is equal to 1, that is the area under this curve. So this area is actually 1. Okay, the next thing that we learned was a normal distribution. Alright, so what did we learn about normal distributions? We learned the PDF. So how does the PDF look like? It is 1 by sigma root 2 pi e to the power minus half x minus mu by sigma whole square. Okay, so x follows normal, mu sigma square, where expectation of x is mu and variance of x is sigma square. Alright, and if I have to find out the CDF, I should consult online tables or some software. Okay, because it is a little complicated analytic to find it out analytically. And if we transform this variable, so let's say if we consider a variable y, which is x minus mu by sigma, then y follows a normal 0, 1. So any normal distribution with mean 0 and variance 1 is called a standard normal distribution. Okay, this is a standard normal distribution. So if we put mean equal to mu equal to 0 here and sigma equal to 1 here, we are going to get a probability distribution of a standard normal. So standard normal 0 1 would be 1, fx would be 1 by sigma is 1, so we would have root 2 pi e to the power minus half x minus mu, mu is 0 and sigma is 1, so it would be x square. Alright, and expectation of x is 0, variance of x is 1. Okay, now why is this standard normal important? Because standard normal, this distribution is the CDFs are given as tables. So if we have any other normal distribution in our hand and we want to find out the area under the curve or above the curve, we can do that using the tables as well. Nowadays, see, we have softwares. It's not an issue. But you imagine when this was first, the inception of this distribution happened, calculating this thing was a very difficult thing. Comparatively, any calculation with these PDF was relatively easier, and the tables that were standard normal tables and any distribution tables that we have now, those were initially computed by hand. So those if you are provided with offline tables in any case, then that table usually corresponds to a standard normal distribution table, and if you have to find out some values based on the original distribution, you can always convert, alright, and get those values. Okay, what else did we learn about properties of the continuous random of the normal distribution? So let's say we are talking about properties. Okay, so here we have, let's say, two normal distribution. This one, okay, this is a bell-shaped distribution, and also we have another bell-shaped distribution like this. Okay, so here this is for both of them. For this distribution, this, let's say, follows mu1 sigma 1 square, and this distribution follows normal mu2 sigma 2 square. So what is the relation between mu1 mu2 and sigma 1 sigma 2? Can anybody say? So here in this case, mu1 equal to mu2 equal to mu. Okay, but what is the relation between sigma 1 square and sigma 2 square? Is it greater than, less than, equal to? What is it? So what does this sigma 1 or sigma 2 imply? These are, so sigma 1 is the standard deviation and sigma square is the variance, which is a measure of spread. Okay, so you see, for this I'm going to use a different line for this color. Okay, so the blue curve, the spread of this blue curve is from here to here. Okay, so this is okay, so this is a representation of sigma 2, whereas sigma 1 is measuring the spread from here to here. This is, in some sort, the spread is being represented by sigma 1. So here the spread is less, it's less dispersed. For this blue one, the values are more dispersed. On our x-axis we have the x's. So here, let's say my x is very large, but the probability is relatively less. So getting something as extreme as 10 is possible if I assume that this point is coming from this distribution. But if I say, like, if I have this distribution, get the probability of having a value which is as greater as large as 10, that is very low. Okay, so in such cases the spread of this distribution, okay, is way less than the spread of this blue distribution. Okay, so if I have these are all relative quantities. If sigma 1, so here what can we say? We can say that sigma 1 square is less than sigma 2 square. That is, the variance of this red curve is less than the variance of the blue curve. And also one more thing we should note that mu and sigma are independent quantities. So we cannot make any comments on how the distribution will be if we know one. So let's say I know the value of sigma, but there's no way I can predict what should be the value of mu based on the sigma, because these two are independent parameters. Alright. And also one more thing we should note is that if we have a standard normal curve, let's say this one, or let's say this is a curve, we have fx and we have x along this line, and this follows a normal mu sigma square. So here the symmetry, the center point would be mu. Okay, so now if we draw lines like this, let's say these are equidistant lines. Alright, this is mu minus sigma, this is mu plus sigma, this is mu minus 2 sigma, and this is mu plus 2 sigma, and let's say this is so this is mu minus 3 sigma, and this is mu plus 3 sigma. So if this is a normal distribution, then this area is actually approximately 68%. Alright, this area from mu minus 2 sigma to mu plus 2 sigma, this entire area is close to 95%. Okay, and getting something let's say this area from this mu minus 3 sigma to mu plus 2 sigma, this entire area is actually greater than 97%. Sorry, 99.7%. Okay, this is something which you should remember. So if I have to write it down, so probability mu minus 3 sigma less than x less than mu plus 3 sigma is equal to 0.997. Okay, similarly probability mu minus sigma less than x less than mu plus sigma, it is approximately 0.68. And again here mu minus 2 sigma less than equal to x less than equal to mu plus 2 sigma, this probability is close to 0.95. Alright. Okay. And what else did we learn? So if, let's say, x is a normally distributed random variable, then ax plus b is also a y equal to ax plus b is also a normally distributed random variable. Okay, so x is y is ax plus b, then expectation of y would be a of expectation of x plus b, and variance of y would be a square variance of x. Alright, so this will be a mu plus b, and this would be a square sigma square. So then y would also follow a normal distribution with a mu plus b mean, and a square sigma square would be its variance. Okay, is this clear? Any questions so far? Alright. Oh, yes, you were saying something, sir?
You can continue.
Oh, okay. Fine. So we learned this. Now, another important thing that we can exploit about these normal distribution is its symmetric nature. Okay, this is something which is very useful in solving the questions. So this is symmetric normal distribution. Normal mu sigma square is symmetric about mean mu. Alright, so if I have a distribution like this, let's say x follows normal mu sigma square. Okay, if I write a variable like this, x minus mu by sigma, then this follows a standard normal distribution. Okay, so this also, since it's a normal distribution, it is symmetric, and the point of symmetry is 0. So the standard normal curve looks like this. this is the point 0, and this is going towards plus infinity, this way it's going towards minus infinity. Alright, now if I want to find area under this point, let's say this is my point A. Okay, so area below this point A would be equal to area above this point minus A. So let's say here A is minus 2. Alright, so if I choose one point over here, area below this point would be equal to the area above the reflection of this point along the y equal to 0 line. That is, this area and this area is the same thing. Okay. So this is one such important property that we want to find out. Let's say we want to also find out something like this. We have a curve. This is a standard normal distribution. We want to find out probability mod x greater than, let's say, 0.3. This means what? Probability either x is greater than 0.3 or probability x is less than minus 0.3. Okay, so this one we can write as 2 into probability x greater than 0.3. Here we have 0.3, here we have minus 0.3. So we actually wanted the area above this line and below this line. Since these are equal, if we have information on any one of these areas, then we just need to double it up, exploiting the symmetric nature of this curve, and then we have the results. Okay. So how is this actually used in questions? That thing we'll discuss little later, but so if you have been given a problem like this, x follows normal mu sigma square, and you have been told to find probability a less than equal to x less than equal to b, let's say. So the first thing that you should do is, one thing is very straightforward. You know these values, you just calculate this would be how much. This would be probability x less than equal to b minus probability x less than equal to a. So what I am doing, essentially, this is my b and this is my a. First I am calculating the probability till b, sorry, and then I am subtracting this part, probability till a. Then I am getting the required probability that I have. So I can readily go ahead and do this. But with softwares it's very easy to do. But if you have to do it analytically, sometimes you can also do it like this. So this you can write as probability. You can transform it into x minus mu. So this would be a minus mu less than equal to b minus mu. This you can write as probability a minus mu by sigma less than equal to x minus mu by sigma less than equal to b minus mu by sigma. Okay. So the signs won't change because sigma is always a positive quantity. Alright. So this one you can write as probability a minus mu by sigma less than equal to, this quantity is usually what is known as it is denoted by z or z. Okay. So z less than equal to b minus mu by sigma. Okay. So now this one, this z1 corresponds to a standard normal distribution. So following this similar logic, we can write this as probability z less than equal to b minus mu by sigma minus probability z less than equal to a minus mu by sigma. Okay. And this thing, probability z less than equal to a minus mu by sigma or probability z less than equal to b minus mu by sigma. So this thing is denoted by capital phi of a minus mu by sigma, where this phi is actually the CDF of a standard normal distribution, and these values are usually given in tables. Okay. So whenever if you see something like phi, you just immediately have to think that phi, this means it is probability z less than a minus mu by sigma. Okay. So as we solve more and more problems, these would be clearer. Okay. And also another important result we learnt is that this is a property, or rather this is a result. If we have, let's say, x1, x2 and n random Rn randomly distributed normal random variables, and they are independent. This is very important. They are independent. Then any linear combination, okay, let's say I will demonstrate, I will write it initially with 2. Let x1, x2 be independently distributed. Okay, 1 second, I'll just write it properly so that it's okay. So the result is if x1 and x2 are both normal distributions with mu1 sigma 1 square and mu2 sigma 2 square, okay, and they are independent, then any linear combination of x1 and x2 will also follow a normal distribution. Okay. So let's say if I have something like this, x follows normal 2, 2 and y follows normal 3, 5. Since both are, and I want to find out the distribution of z or p equal to 2x plus y. Okay, so it could be anything of the format cx plus dy. Okay, where c and d can take any numbers. Okay, c, d can belong to any number in the real line. So if I have something like this, then this cx plus dy is actually a linear combination of x and y. So any linear combination of two independent, or any, even if it is dependent, of two random normal variables is always normal. And if they are independent, here I am saying they are independent, then if they are independent, then we can easily write the parameters as this. So x follows, I said, normal 2 2, y follows normal 3 5. So this is mu1, this is sigma 1 square, this is mu2, and this is sigma 2 square. And I wanted to find out 2x plus y, which is of the form cx plus dy. Alright, so p also follows a normal distribution. This much we know. Now what are the parameters of p? So expectation of p is how much? It is expectation of 2x plus y. So it is 2 into expectation of x plus expectation of y. So that would be 2 into 2, 4, plus 3, that is 7. Okay, and variance of p would be variance of 2x plus y. Now usually this would be 4 variance of x plus variance of y plus 2 covariance of 2 into 2 covariance of xy. Since we have said that x and y are independent, therefore covariance between x and y will be equal to 0. This will only hold when x and y's are independent. So then this would become 4 variance of x plus variance of y, and that would be 4 into 2 plus 3, it is 8 plus 3, 11. So p would be normally distributed with mean 7 and variance sigma square equal to 11. Alright. So extending this result, if we have, let's say, x1, x2 and xn independent normal variables, then x1 plus x2 plus xn will also follow a normal distribution, where this would be summation mu1 mu square, sorry, this would be, let's say each xi follows normal mu and sigma square. So here this would follow n mu, and this would follow n sigma square. Okay, so x bar would be 1 by n summation xi. Okay, summation xi is this thing, okay, which is n following n mu n sigma square, because we are expectation of y would be expectation of x1 plus expectation of x2 till expectation of xn, so it will be n times mu. Alright, and variance of y would be variance of x1 plus variance of x2 plus variance of xn. There wouldn't be any pairwise covariance terms because these are independent normal variables. Okay, so then n times sigma square, that would be n sigma square. Now if I have to find out the mean, okay, so then the sample mean x bar would be 1 by n summation xi. Expectation of x bar would be 1 by n expectation of summation xi, that is how much? N mu. So this would be 1 by n into n mu, that is mu, and again variance of x bar would be variance of 1 by n summation xi. So this would be how much? This would be 1 by n square into variance of summation xi. Now variance of summation xi is how much? N sigma square. So this would be 1 by n square into n sigma square. So we would have sigma square by n. Okay. So the result is that if x1, x2 and xn follows normal mu sigma square and they are independent, so such cases where independence also holds and each components are coming from the same distribution with the same parameters, we say that these are IID, identical and independently distributed. Okay, so this sample
Madam, can you just elaborate what is IID, independent and
yes,
identically distributed?
Yes, so each of these xi's, they are from the same distribution, so they are identically distributed. Okay, and I am saying that these are independent samples. Whatever value of x2 is coming, okay, is not dependent on the value of xn. For example, let's say I am choosing or let's say xib, my let's say xib weight, okay, of ith, not exactly ith, my xi, let's say the random variable is weight of an individual, okay, and yi is also, let's say, some associated quantity, okay, something which is similar to weight, but let's say this is height. Okay, now if I see that the distribution of weight and the distribution of height is the same thing, then I mean if they are identically distributed, if this is also normal 1 1 and this is also coming from a normal 1 1 distribution, so then x and y are identical, and your if it so happens that your weight is not dependent on what your height would be, then we can say that x and y are independent and identically distributed. Alright, but in this case it will not work because usually your weight is dependent on height. Okay, but if it happens that what this variable and this variable are totally independent, then we can say that these are independent and identically distributed. Okay, so height weight is not a good example. Let's say I'll give another example.
Madam, if considering only a classroom in which there are many students, so we want to come to an inference that no person in the classroom has more than 2 siblings. So to do that one, I should collect the data about the persons or the students who are having how many siblings they have. That data should be collected instead of collecting the height of the data or the weight of the data or the mass of the data. So what is relevant to that particular inference, only that data is taken. Like
yes,
exactly. Yeah, can I relate that one to the identical and independently distributed data? That kind something like that.
Can you repeat your question?
Like height of in a classroom, I want to come to a conclusion that no person is having more than 2 siblings. Okay. So for that one, I'm going to collect the number of siblings of each person in the classroom. I'll not be collecting the data about the height or weight or the mass of the student.
No, see, exactly. So whatever you are trying to measure, that thing you have to get.
Yeah,
So
is that correspondence to IIT? Can I relate that to
no,
IIT?
that is
Like,
not
because
actually, no, that is not IIT. IIT means if you have variables like these which are coming from the same distribution and they are independent. One is not dependent
they
on
are
either. Let's say x1 is your marks on uh, some subject. Let's say marks in science, okay, and x2 is your marks in some physical education.
okay.
All right. So if I assume that your marks in science is not dependent on your marks in physical education, then these two variables are independent. Okay. And now I collect, let's say you have 100 students in
Okay.
the classroom that you want. So x11 would be marks of student 1 in science, x12 would be marks of student 2 in science. Like that you would have x100, and similarly you would have x21, x22 and x200. So these would be marks of 100 students in science, and this would be marks of 100 students in, let's say, physical education. Now you plot this graph, okay, this distribution and this distribution. If you just plot 100 points, and if you see that this, for physical education, the graph is something like this, okay, and for maths also the graph is very similar. Somewhere it's overlapping and somewhere it's this. So you are getting similar curves around the same. Let's say the mean marks is 60 for each of the subjects. All right. So here along this you are going to plot the relative frequencies, or I mean how many people have got. So the way to get this curve is that you are going to plot histograms, okay. Let's say 10 to 20, 0 to 10, 30, 30 to 40, 40 to 60, 60 to 70, and then 100, okay. So your histogram will be something like this. This is the histogram that you have. Let's say it looks very symmetric. This is approximated by the normal curve, whatever I am showing on your left, okay. Now if you see that, this is your marks in science, okay, and the histogram that you have for physical education, okay, 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 60, 70, 80, 100. This is also very similar, okay, with similar kind of shape, similar kind of probabilities on the y-axis. So y-axis would actually give you the relative frequencies, right? So that would be how much, let's say between 30 to 40, 5 children have got it. So relative frequency would be 5 by 100 for that matter, right? So here also if you see between 20 to 30, 5 people have got it, okay, and the curve is normally distributed like this, approximation, it's symmetric. So if this histogram or this distribution matches with this distribution, and we assume that marks in science is no way related to marks in physical education, both are independent quantities, then these two variables, marks in science and marks in physical education, are IIDs. They are identically distributed, but they are independent. Is it clear?
Okay. Okay, madam.
Okay. All right. So this thing you have to keep in mind. The variables are identically and independently distributed. We have to collect observations on the variable, and we have to see whether that it is conforming to the underlying distribution that we have in mind, okay. Alright, I hope this is clear to you. Alright, so apart from this, we also learnt about approximations. Okay, what were the approximations that we learnt about? The first thing was binomial approximation to normal. Now any binomial distribution can be approximated to a normal distribution provided n is large. Okay, and in such cases, let's say if we have probability x less than equal to x, we can write it as, since we are approximating a binomial distribution with a curve, we have to apply for a continuity correction module. So we have to write here less than equal to x plus 0.5, and that would be probability z less than equal to, now z would be how much? Z is actually x minus mu by sigma. So mu for a binomial distribution is np, and sigma for a binomial distribution is npq. So this would be z less than equal to x plus 0.5 minus np by root over npq, okay, where q is nothing but 1 minus p. Alright, so then we can write this as phi of x plus 0.5 minus np by root npq, and this value we can get from tables or we can get directly using the softwares. Alright, okay. Another important thing when it comes to R is that whenever you are, suppose I am going to do a p norm of x, mu equal to 0, I have to ensure that here what I am entering is not variance, not sigma square, but sigma. This thing is very crucial. Okay, usually by default if we don't add anything, we would get a standard normal curve. But if we, so let's say if I have been asked to find out probability x less than equal to 5, where x follows normal to 25, I should enter p norm x equal to 2, mu equal to, x equal to 5, mu equal to 2, and SD equal to 5, not 25. Alright, so this thing we have to be very careful about. Usually when you find something normal, the second parameter, that is always sigma square, but R is going to take sigma as input. So this conversion we have to do before we feed our values in R. Is it okay? So now let us move on to few of the problems. So as I was saying, this one is a binomial approximation to normal, and the last thing that we learned was Poisson approximation to normal. Okay. So here also if we have something like this, let's say probability x less than equal to x, we have to write it as, so then the transformed variable z would be x minus mu by sigma. So for Poisson, mu is lambda, variance is also lambda, so sigma is root lambda in this case. So here we have to write it as probability z less than equal to x minus mu, so here again we have to apply that continuity correction, x plus 0.5 minus lambda by root lambda, and then this would be phi of x plus 0.5 minus lambda by root lambda. Alright, so given this, we are going to now solve a few problems. Okay, let's say this one. We'll start with this. Okay, so if x is uniformly distributed over the interval 0 to 20, the probability that 2 less than x less than 7 and x greater than 6 are how much? Okay, so x is uniformly distributed over 0 to 20. So x is uniform over 0 to 20. Okay, so fx is how much? Fx is 1 by 20 when 0 less than equal to x less than equal to 20 and 0 otherwise. So probability 2 less than x less than 7, probability 2 less than x less than 7 would be how much? Would be 2 to 7, 1 by 20 dx. Now how did I write this? So see, this is uniformly distributed over 0 to 20. So from 0 to 20, the graph is this thing. Now I want area between 2 and 7. So I am just writing the fx value over here, and then from 2 to 7 I am going to integrate. So this would give me 5 by 20, that is 1 by 4. Okay, and then probability x greater than 6, this would be 6 to 20, 1 by 20 dx. So this would be 1 by 20, 20 minus 6 is 14, this would be 7 by 10. So the answer is answer B. Is it okay? Any doubt? Okay, so then we'll move on to the next one. Again they are saying x is uniformly distributed over 0 to 20. Probabilities that 1 less than 6, like x less than 6 and x less than 8 are how much? So same thing, this is the probability, this is fx, this is 1 by 20 from 0 to 20, and then it's 0. So probability 1 less than x less than 6 is how much? It would be 1 to 6, 1 by 20 dx. So this is also 5 by 20, that is 1 by 4. And probability x less than 8 is 0 to 8, 1 by 20 dx. So this is 8 by 20, that is 2 by 5. So this is the answer. Alright, moving on. So here they are saying metro trains arrive at a specified stop at 15 minutes intervals starting from 8 am. That is, they arrive at 8, 8:15, 8:30, 8:40. If a passenger arrives at the stop at a time that is uniformly distributed between 8 to 8:30, what is the possibility that the passenger waits for less than 5 minutes for a metro train? Okay. So trains arrive at specified stop at 15-minute intervals starting at 8 am. That is 8. If a passenger arrives at a stop at a time that is uniformly distributed between 8 to 8:30, then the probability passenger waits for less than 5 minutes. Yes, I think Janvi has a question. Yes, Janvi.
Ma'am, please repeat the second question you just.
Second question, this one.
Yes, yes.
Oh, okay. So, if X is uniform, so which part are you facing problems?
Ma'am, I didn't get this from the starting. Please.
From the starting.
Yes.
Okay. So, right from here, you had a problem.
Uh, no, ma'am. Skip that part. At the end of the solution, you can start from there also. Means uh, probability at less than 8 from this step.
Okay. So, probability less than 8. Now, probability X less than 8 is actually area under the curve of fx
Hmm.
in the range, wherever the range starts from, till 8. Now, you have to, this is your fx curve, okay? It is
Okay.
taking the value 1 by 20 from 0 to 20, and then it is taking 0. So now you have to find out probability x less than equal to 8 or less than 8. It means, okay, one more thing is, since x is continuous, probability
Yes.
x less than 8 is the same as probability x less than equal to 8, because individual point probabilities are 0. Okay.
Okay.
Okay. Now x less than equal to 8 means this is along your x axis is x, along your y axis is your PDF fx. This means that till your 8, whatever is the area under this curve, this is actually your probability x less than equal to 8.
Okay.
Okay. So here this is a shape of a rectangle. We can do 8 minus 0, 8 into 20, and readily we can get the answer. But generally how we should write, we are integrating fx from 0 to 8, fx dx. So fx is how much here? Fx is 1 by 20 when 0 less than x less than 8 and 0 otherwise. Okay. So we are writing 0 to 8, 1 by 20 dx. So this would be 1 by 20, 0 to 8 dx. So this would be 1 by 20x from 0
Ma'am,
to 8.
ma'am, how this value is coming? 1 by 20. This constant is coming from direct from the uh, derivation, or it is given in the question.
In
Um,
the question it is given x is uniformly distributed over the interval 0
okay.
to
Okay.
20. So it
Okay.
is given x uniformly distributed from A to B. It means that between A and B, this PDF fx would be 1 by b minus a. Only then
Okay.
we have this condition, no, integration of fx
Okay.
dx minus infinity to infinity, this has to be equal to 1. This is
Okay.
one of the
Now
conditions that
clear,
has to
ma'am.
hold. So if this is a uniform distribution between A and B, this density has to be 1 by b minus a. So since here it is mentioned that it is uniformly distributed from 0 to 20, the fx value is 1 by 20 from 0 to 20 and 0 elsewhere.
Okay. Thank you, ma'am. Clear now.
Clear now, no?
Okay.
Okay, fine.
You can proceed.
Okay, fine. So we were here. Metro trains arrive at a specified stop at 15 minutes intervals, and this happens. So how should we frame this question? If a passenger arrives at a storm at the stop at a time that is uniformly distributed between 8 and 8:30, the probability that a passenger waits for less than 5 minutes for a metro train is how much? Okay, so let x be the time of arrival. Okay, and between x like 8 to 8:30, so this is the uniform distribution that we are talking about. Alright, so this is your arrival time. So so x is not time of arrival. X is how much wait time a person has to wait. Okay, 1 second. Let x be that number of minutes past 8 am a passenger comes to bus stop or metro stop. Okay, so anywhere so x is actually arrival time, so the person can arrive any time between 8 to 8:30. Okay, and the probability that has to wait for less than 5 minutes for a metro train. So trains are available at 8, 8:15, 8:30, 8:45. Okay, 15 minutes interval. So from 8 to 8:30 there are 3 trains. Okay, so a passenger waits for less than 5 minutes for a metro train. This will happen only when the passenger arrives any time from 8:10 to, let's say, 8 uh, The question is the probability the passenger waits for less than 5 minutes for a train. So she has the probability that she waits for less than 5 minutes for a metro train is that he arrives either at 8:10 and or he arrives somewhere between 8:25 to 8:30. Okay, so then the required probability is probability 0 or sorry so this is this area that x is lying between 8:10 to 8:15, either this thing or probability he has arrived between 8:25 and 8:30. So only under these two criterias the passenger has to wait for less than 5 minutes. Okay, so here if this is 0 to 30 minutes, this would be 10 to 15 and this would be 25 to 30. So the required probability would be 1 by 30 from 10 to 15 dx plus 25 to 30 1 by 30 dx. So this would be 5 by 30 plus 5 by 30, that is 10 by 30, which is equal to 1 by 3. Is it clear? So if I have to write it clearly, let's say this is x. Okay, this is your 0 and this is 30 minutes. Alright, this point corresponds to 8 o'clock, this point corresponds to 8:15 and this point corresponds to 8:30. Alright, and let's say x is the time of arrival or minutes past 8 o'clock in which passenger arrives, and that is uniformly distributed, you have been said, between 0 to 30. So this fx is 1 by 30. Now the passenger has to wait for less than 15 minutes for a metro if only if he arrives at 8:10 at or after 8:10 and catches the metro at 8:15, so that would be his waiting time 5 minutes, or if he arrives at somewhere between 8:25 and 8:30. Okay, so this would along this is 10 minutes and this is 25 minutes. So the required probability is then 10 to 15 fx dx plus 25 to 30 fx dx. So this is 10 to 15 1 by 30 dx plus 25 to 30 1 by 30 dx. So this x would be 5 by 30, 5 by 30, and so we have 1 by 3 as answer. Is it clear? Is it okay? Any doubt? No? Okay. So here again we have the same question, but then now the question is, find the probability that the passenger waits for at least 12 minutes for a metro train. So here again, this is 0 to 30. So he has to wait for at least 12 minutes. So to wait for at least 12 minutes, he has to arrive, let's say this is at 8:15, there is one train. So at least 12 minutes means he has to arrive on or before 8:03. Okay, and if he just passes this, like he missed the 8:15 bus and he arrives at least after from 8:15 onwards till, let's say, 12 minutes, no? So 30 minus 12 would be how many? How much? 18. So 8:18. Alright, so then he has to arrive either from 8 to 8:03 or between 8:15 and 8:18. So that would be 0 to 3 fx dx plus 15 to 18 fx dx. So this would be 3 by 30 plus 3 by 30. This would be 6 by 30. That would be 1 by 5. And that is the answer. Is it clear? I hope I'm still connected. Is it clear? I think. Any doubt if you have, please ask.
Madam, when the video will be uploaded, this recording will be uploaded?
The recording, right after the session, I'll start the upload. Actually, it takes a little while to process it and upload. At least 3-4 hours it takes. So I would request you to be a little
by
patient.
today evening, like by night 10 o'clock, it will be available.
Yeah, it is supposed to be available until and unless there's some network issue. Okay, I'll put it on update
By tomorrow?
right after. Yeah,
Tomorrow
definitely
morning
by
it will be
tomorrow. Yes.
Okay.
Okay. If there are no other questions, then I'm going to close this session. Thank you so much for joining, and I'll see you next week. And if you do have questions, please let me know now, or you can even send mails later.
Thank you.
Okay. Thank you so much, sir and ma'am, everybody for joining, and I'll see you next week. Bye bye.